Fantastic. Well, it's great, to join these calls when we're chatting about it. I think I um, I guess I'm in the company of peers when I look at people around the call, and a lot of you are veterans in these different spaces and all that. So I'm just here to share my experiences. It's not, we're not nobody is a mountain of wisdom in this, but on the semiconductor side, I've tried to capture a few things on these slides because the world has the as you know, things go in circles, right? If I look at telecom era, for example, we had the situation where in those days I had a session for BSIA folks talking about how in the telecom era all the systems were developed in a co-designed fashion, semiconductor, software, all of the things like when Nortel was building things. I worked for Nortel for about 7 years, 8 years, and when we were building these systems, these optical systems, everything was co-designed together. Even we had foundries for our technology, and every country had its own service provider that drove the specifications for those things. And when the world turned upside down with hyperscalers joining, the entire notion of co-design was disaggregated, and all these elements became different ecosystems. TSMC was born. There was multiple other elements were born together, and now we see that thing coming full circle with AI, where the requirements of AI is so that's one, two orders of magnitude larger than any existing system. And as a result of that, people are going back to those Nortel days and saying, well, we have to build a whole system together, like NVIDIA and others. So I had a few charts to talk through that, but I'm not sure how many people on the line are electrical engineers, but just thought maybe when we talk about semiconductors, it's good to see what they are. So if you look through just from a definition perspective, semiconductors are. Let me just get a little pointer here as well, if I can. Uh, no draw. Where's the point? Where's the pointer? Spotlight or let's see. There it is. Mouse. Okay, you can see my mouse as well now.
Yeah.
Looks pretty small, but that's okay. So if you look at semiconductors, they fit somewhere in between conductors and insulators, right? Conductors being like wires and what have you. There's two bands, the valence band and conduction band, and when these two bands overlap, you have a conductor, so electrons could move freely between these folks. If they're too far apart, then you can't, there's no electron movement here, so you won't have any conduction. And semiconductors have brought these two things close together, so with thermal and other attributes, you can make the electrons jump up and down. So in a way, you have a gate that you can apply something, and then the electrons move and becomes conductor. And there's many different elements, that you have in semiconductor. I wrote a few of those things: silicon, germanium, compounds and so forth, cadmium, selenide, and other things that create semiconductors. And this semiconductor ecosystem has gone through evolution, significant evolution since 1970s, that it got a hold in the market there. And there's an element that is introduced in semiconductor, which is the doping, which makes this different characteristics for these semiconductors. So that was just a definition piece for those who will be watching online later on. But if I look at the industrial revolution, semiconductors created the third revolution. The first one was, as you know, in the 1780s was when steam engines were created, and that really moved the production forward in a significant way. Then the second industrial revolution came when electrification happened and led to mass production through assembly lines and what have you. And then semiconductors came along, and in the 70s, and then computers were created, electronics and all the things that you see. And as they were developing these things, of course, globalization took effect, where you start offshoring production to low-cost economies, and that sort of made the world a little bit flat in a way. And then IP and everything else start traveling across the world, and TSMC was created. Other things you see in China and other elements were put together, and now we're in this digitalization, which is quite advanced. This Industry 4.0, AI, and everything else that you hear about. Now, one element of this is that every time you do this type of innovation, that you go through you have to almost reinvent the previous cycles. So, for example, for the AI to take place, semiconductor has to be reinvented. Electrification has to be reinvented, and I guess we don't use steam, for production anymore. But you have to go back and reinvent things to take the next step forward, because the specifications change. So it is not a continuous line. I tried to draw that over the weekend, and I gave it to ChatGPT. I said, "Could you make this diagram clean?" You should have seen what I got out. It was after half an hour of work, I got garbage out, and even though he was explaining to me that he's doing it the right way, I said, just take what I've drawn by hand and make it into a graph. And I couldn't get it done. So sorry about that. You just have to bear with my my analogy and not see a beautiful chart. One other thing I would say, for those of you who may be enthusiasts in semiconductor, there's a very well known book written by Chris Miller called Chip War. I would highly recommend reading this. I mean, you see right now chip companies and semiconductor companies are outperforming the market by a significant amount. And some of you might have already benefited from that through your private placements or public shares you bought in NVIDIA or Oracle or other players in there that use semiconductors. It's a very, very good, well-written book talking about how this whole thing came about and why we are here. And of course, Taiwan being at the center of it, I travel quite regularly there, based on our customers and our suppliers, and it's incredible how this tiny island, it is almost like a military-run uh, entity. When TSMC says we're going to do this, everybody lines up, like 30, 40 companies in the ecosystem line up, and they execute without asking for business plans and is this going to make any money? Well, and last, I think it was three weeks ago, I was there, and I was just chatting with somebody in TSMC, and they told me something very, very thought-provoking. And they said, well, we don't try to predict the future. And we hear everybody's opinion about the future of this is going to happen, and we're going to do this technology, that technology, and we listen to everyone, but we only make our decisions based on our largest company, largest customers telling us to do something. That's interesting, huh? If you think about North America, we don't do that. We basically reward innovation. Let's come up with radical thinking and do this, do that, all of these things, right? And one out of, I don't know, 1,000 of these ideas succeed. So it's a very telling story of how over the years, following your customer lead, and how, of course, you're not going to be at the leading edge of technology because your customer may take time for them to come up with something, but you can mobilize an ecosystem behind you to accelerate once the idea catches on, to accelerate and become the first in the world. In the area that we work in RANOVUS, I'll talk a little bit about that, but it's around packaging, miniaturizing optical interconnect chips. That used to be in big systems and in tiny chips, and putting them into maybe I'll show you some. I do some show and tell as well for you guys. So this is, for example, an 800 gigabits per second chip that we've developed, and we put it inside GPUs. We co-package them with GPUs, our chips around, so fiber comes out of the GPUs, and that gets connected to other, so it replaces copper in a way, but at much, much higher capacity. This field, which was made possible by building optical components using silicon, is called silicon photonics, and I guess last year when I was in Taiwan, they had the kickoff session that they had for the Silicon Photonic initiative in Taiwan, and they had 30 companies line up from Taiwan ecosystem presenting their commitment to drive this initiative and be a be a massive player in this area. And we were the only private company on the panel. There was bigger companies as well. The whole day session was quite intense dialogue. All the big players were there, and it was interesting that this year when I went to the same conference in September, early September, the I think the room was about, I'd say probably about 2,000 people were in the room in the audience, and then they were broadcasting it everywhere, and you could see that the ecosystem had flourished over a year and had accelerated in a way to become dominant. So these are some lessons for Canada to learn in terms of how we can get there. But very briefly, going through just a few more charts to set the context on how AI has transformed the requirements. You see the Web 2.0, these are the hyperscalers. The drawing you see on the right-hand side is a traditional data center from Meta. And all those circles you see, those are all switches. The connections you see between the switches are optical components that connect them together. So each of the gray ones you see at the bottom are a rack, and on top of it is a switch. So a massive, massive infrastructure carrying more traffic in one of their data centers than the entire AT&T network. So when they came to play, they had these traditional servers they were building, traditional switches, and they were connecting them all together to work there. And now, if you look at the traffic of that area, if you look at now what an AI data center added to that data center was this backend section, which has these compute accelerators. These are GPUs connected to switches using copper, and then each of these nodes are connected through another backend switch to other places. So all of a sudden, a whole new category of chips had to be designed, and switches and things of that nature, which now a lot of people like NVIDIA, AMD, and hyperscalers are working in that space. Now, the interesting part that is through that transition is that if you look at the connectivity requirement of the traditional data centers for hyperscalers, if you normalize it to one, you're looking at 100x more bandwidth between GPUs and 10x more bandwidth between the racks. So you cannot do this orders of magnitude in engineering. You cannot do these orders of magnitude without significant disruption. This initiative, we started it in 2019. So you can see it's a long, long time ago, right? To get to an intercept point that when it becomes ready for the market, it can take off. So this is really, one of the things that has happened and we work in these spaces, basically in these places, building those miniaturized technologies with high bandwidth, and it's all manufactured here in Canada. We have a laser foundry in Ottawa that builds our lasers, and the silicon photonic components and high-speed mixed signal comes from Albany, New York. One of our foundries, Global Foundries, is there. But we do all the packaging, all of that, all the things that you saw is done in Ottawa, and which was a center of excellence for optics since Nortel and JDSU days. So the AI compute system, these are all semiconductor folks and hyperscalers. These guys, the NVIDIA and AMD. This is one of our products in the market. There are other people like these other folks you see, hyperscalers. Now they're thinking, well, it's good that NVIDIA can charge them, let's say for the chip itself is like $5,000. They put it into a shelf, it becomes $250,000. They put it in a rack, it becomes $5 million, right? And the incremental cost of each of these stages is very little. But at the same time, they benefit from that one thing they have, and then they co-design the entire thing to have a very, very high gross margin on business. Of course, hyperscalers don't want that. They don't want to be in an NVIDIA prison, they call it. So they design their own chips. They don't design their own chips, and then they get people like MediaTek, which is one of our customers, the Taiwanese. You guys might know MediaTek and other things as well. They They do a lot of custom chips. Broadcom is another one that does custom chips. So there's a whole group of people developing their own custom chips and their own custom systems to compete with AMD and NVIDIA. And these are the end users. So that's one element. Now, all of these things I mentioned, they're all at chip level, at die level. So there's a die in the middle, there's one die, and then there's chips around it to allow the I/O for this chip input output to come optically. So what we've also done with DARPA, we've won a big contract with DARPA in the US to do a wafer scale optical package. So actually, I advantages of having it here is that I can show it to you. So this is the wafer scale version of that. So as you know, Cerebras is you might know that they have they just recently raised $1 billion for their wafer scale GPU. So they have wafers that have 78 GPUs on it, and they're all at a wafer scale. They're not individual. They're all connected together. But for the middle GPUs to get their traffic out, they need to have an optical chip that goes on top of this so that it provides the highway for the for the information to come out. And that's what we built. We built and we do a co-packaging. This is a technology that is going to disrupt NVIDIA and everybody pretty much. And it's a couple of years down the road, in about like 3 years or so. But we've won this contract with them through DARPA. And now that Canada is interested in defense, they're actually surprised that DARPA awarded a Canadian company something like that. And I, good dialogues with the Minister of Defense and others to see how we can have a similar things in DARPA for Canada. So I guess maybe I'll jump over the next things in the interest of time. We talked about this AI rewinding the clock. Like if you look at its systems, co-design of foundries, these are the hyperscalers. AMD bought this company called ZT System to build systems themselves. Silo AI for software. NVIDIA has a full stack. In the foundry and OSAT, TSMC is the king, and there's a whole bunch of people designing custom chips for these people on top. And if you look at it, some of these companies are growing in stature, like Broadcom, NVIDIA, TSMC, and all that, and they start to change the dynamics of the market. So if I look at in the future, I look at some of these players and how much is their market cap. You see the numbers are quite large. And the fact that they have such a high valuation in the market and a lot of cash at hand has created almost a circular economy. You might have heard about this. This is my last chart, seeing how they fuel this flywheel of AI. And I think this one is a very this one comes from Bloomberg, I think. Let me see. Yeah, it's from Bloomberg. And it shows each of these companies, like NVIDIA, and how their investments go into people like CoreWeave, and then CoreWeave purchases back equipment from NVIDIA. For those of you who were in telecom days, you might have remembered this, where Nortel and Lucent were giving loans to their customers to buy their equipment, and then those companies will go raise money in the market based on the fact that they have Nortel equipment, but there was no demand for the traffic for those type of equipment in terms of service provider demand. So they would go bankrupt, and then that led to a lot of financial disaster. The difference now is people are all asking the question: is this a bubble? And the narrative that is coming out, which we have some customers in this page and that we're involved with and we're developing things with. I guess the difference is the demand for is coming from these hyperscalers and these big people who have language models they're developing and incorporating that into their business model. Like Microsoft and OpenAI, all these people are doing this XAI, Oracle, and they are the end customers that are building these things. It's not some new player coming in and saying, "Well, I want to build a pan-European network, and I'm a new entrant here, and I'm going to service, give my dark fiber to people," which was Nortel days. These are really big players with a lot of cash, and that's how this thing is working so far. So maybe I pause here. There's a lot of background things here that I tossed there. Hopefully, some of it could be used for a discussion, or if you have any other questions regarding the semiconductor, the systems, the financial market, other things that could be of, I can share some of my opinion based on our experience.
Thank you, Hamid, for that sweep. Very, very, very interesting perspectives.